Hi everyone, I'm Dihu. Welcome to the second part. This tutorials we will give an introduction about audiovisual sound separation. I'm Dihu. I'm from Gaoling School of Artificial Intelligence, Renmin University of China. So we will first give an overview about why using visual information for sound separation. Then we will give an overview about approaches, which are the SOTA approaches and their taxonomy. And finally, we will give a summary about what are the core challenges and future directions in this topic. So firstly, we will give an overview about why using visual information for sound separation. So in a daily scenarios, we will usually suffer from cocktail party problems. That is, there are so many people talking at the same times. Here we have four people. Different people say different words and at the same time. So if we want to know which one's saying what other someone saying about, it's difficult to understand or difficult to separate the sound for the machines. But our human seems to work well on this task. So generally, this task is named as blind source separation in the sound domain. So if we have multiple speaker speaking as a system and recorded by the devices, then for the mixed ones recorded signals, we want to separate the sound for each one. So we want to separate the hello and the next master must for these scenarios. So this is a traditional sound separation tasks. So while using visual information for sound separations, we can see a video for better illustrating this motivation.
拔拔拔拔拔拔拔拔拔。
So when we simply think this man is sleeping far, and if we watching this video,
拔拔拔拔拔拔。
so when we watch this video, we think that this man is saying ba, and actually that's this man is talking the same spoken sound, the same sound, but with different mouth motion. So different mouth motion with of a mouth influence the interpretation of a spoken sound. So this is the McJert effect. This effect shows that the visual information has influence for the sound separation or the sound interpretation. So so under this experience, we think that if we import the visual information, maybe we can improve the sound separation result because visual information is insensitive to audio noise, and also as the video shows, the visual information provide audio context info for interpreting the sound. So that's why using the visual information for sound separation.
拔
So for better show what has the main pipeline for the visual information or audiovisual separation, we show the following three stage for this so under this topic, and this tutorials will go through each topic or each stage in the following sections. First, we will show that in the early stage, the audiovisual separation is going in the is motivated by the signal processing strategies and its blind signal separation as we stated above. Then the researchers propose to model the relation between the sound as motion and using different assumptions, propose different methods to for audiovisual sound separation. And finally, in the current stage, using the deep networks, the research aims to using the learning-based models learn to model the relation between sound and motion and use the build relationship to achieve better audiovisual sound separation. And for this slide, we show that actually in the early stage and the current in the present, most sound separation focus on the speech signal. And the second stage and the second and the third stage focus on the music. And more recently, some approaches aims to separate the natural object sounds for in this task in audiovisual sound separation, because natural sounds is very difficult. It's very difficult. So in the next sections, we will give an overview about the SOTA, about the recent approaches in this topic. And the first one, we will give an overview, an introduction about how to using the signal processing knowledge to separate the sound separation, to separate sounds using audiovisual information. For as in the early stage, the researchers viewed the blind signal separation as a for sound enhancement. So they using the noise filtering technique to achieve blind signal separation. So they have assumption that the speech signal and the noise are assumed to be uncorrelated, and then the observed noise signal X becomes the combination of S and V. So in this condition, the noise is additional noise, and according to the mean square error criterion, the optimal estimator of the signal is obtained by filter S from with the Wiener filter. So in this assumption, Wiener filter aims to minimize the mean square error and then achieve the noise filtering. And the core core contribution is how to, or core challenge is how to build the Wiener filters. And denoise using this Wiener filters to denoise the record sound to the the clean sound. So in this figure, we show that for the noise audio, in the traditional traditional path, and the researchers propose to build an effective filter to filter the noise audio into the enhanced audio. But if we want to import the visual information, in this figure, we can capture the mouse shape, its height and its weight. And using its weight, using the height and weight, we can capture the mouse shape and correlate the mouse shape with the sound. Then using the information here, the visual information, we can better estimate the filter, the Wiener filter, then achieve better audio enhancement for the noise band. And here in the figure in the second figure, we show that using the visual information, we can assist in the audio projection for the filter design by projecting the audio sequence and visual sequence in the same subspace for better capturing the audio information. And another viewpoint is using the independent component analysis to separate the signal different signals from the mixed ones. So the cocktail party problems is there are in this figure there are 5 for source are speaking, and there are 5 microphone are recording, and due to the different position of the different microphones, so the different microphones had different sound recordings for the 5 sources. So we think that each microphone M MG is assumed as a linear mixture of independent component sources. So here the independent components is different sources in the figure, the 5 sources. So each microform is a linear mixture of the sources as the formulation shows. So ICA, the independent component analysis, aims to recover the independent components from the microform array that is S equals W multiply M, and it aims to learn the W matrix to separate the mixture sound M into S. So this is independent component analysis for sound separation in the signal processing viewpoint. So here is how to import the visual information for independent components analysis in audio-visual sound separation tasks. So in this figure, we can find that if the object the object which are producing sound is moving. So using the visual information, we can using it for better for capture the moving source and separate potential have the potential to separating move sources and correct the permutation in audio SAA. Finally, we can it can use the visual information to improve the convergence of SAA algorithm. So this is how to import the visual information for independent components analysis for sound for blind signal separation. So this is the first stage about how to use the signal processing techniques to separate the sound. And the second stage is how to achieve joint audiovisual modeling under different assumptions and derive different techniques. So here the different researchers derived different models such as the graphical dictionary learning and the audiovisual likelihood maximization that aims to modeling the relationship between sound and motion under different assumptions. So for the first one, the graphical models aims to it assumes that different unimodal data are derived from hidden variables, such as audio is derived from S and visual is derived from R. And in this figure, the research considers that the visual hidden variable depends on the audio ones, that is R depends on S. So in this task, it aims to model the relation between the audio and visual as a graphical model, the maximization their correlation in via the designed graphical models. Then in the dictionary learning viewpoint, the researchers consider that they can aims to learn a dictionary by a common dictionary for both audio and visual, then perform correlation learning in these dictionaries by learning the coefficients in the dictionaries. So in the first step, they first perform short-term Fourier transformation or transform from the raw audio waveform into the temporal frequency spectrogram as the colorful image in the left figure. So there are different red parts in the spectrogram, and in the frames we can also see different rectangle in each. So different sound and different sounding objects are correlated. The dictionary learning aims to correlate different sound and different visual object in this as a figure shown. As shown in the figure. So in dictionary learning, it aims to learn to model the audiovisual correlation in a joint audiovisual dictionary learning framework, and it aims that the dictionary dictionary, the coefficient of the dictionary is has different properties, such as the low rank properties. So the low rank property matrix models the background, visual, and the audio information. They assume that the audio, for example, for the visual information, they think that the foreground object and the background information can be separated by the low rank matrix. Then the sparse matrix can extract the sparsely correlated audio and visual components as the figure as shown in the figure. So in the formula, we shown that the first two components is perform the nuclear form for low rank constraint, and the green one, the green rectangle, aims to learn sparse matrix for modeling the correlation between the visual and audio correlations. So in the third one, researcher proposed to maximization the likelihood between the audio and visual audio and visual local features. So in the figure, we show that we can see different circle in the image. The man is playing the violin. So the aims to correlate different local features, such as the circle and the different feature in the audio waveform or the audio spectrogram. So in the formulations, it aims to maximize the matching likelihood between the localized audio and visual features. So for the this works considers that the energy distribution of different sound sources has only little overlap within the beams. So they think that this is a harmony of the audio separation, behind the audio separation tasks. These properties can help to surprise how to train the model in the audiovisual modeling framework. So in this figure, we can see that from the mixture sound separation of sound mixtures, using the model, it can separate the guitar and violin into different spectrograms, and they share little overlap within the beams, as it states this is the harmony properties. And the final one is how to using the maximum posteriors to learning the correlation between the audio and visual modalities for sound separation. So in this viewpoint, under this viewpoint, the sound mixture in the temporal frequency domain is the combination between different sound sources. In this example, it has two sources, and it aims to under these assumptions, it aims to estimate the audio features from the visual features using the MAP criterions, and the most important is the binary mask estimation. By comparing different spectrum of from the mixture from the single source A1 and A2. By comparing each pixel in the temporal frequency domain, the temporal frequency spectrum, it can show that which part or which source is most important or most influence in each locations. So we can generate a binary mask estimation for as a supervision for training the models. So in the figure we show in the right, we have ideal spectrogram, the binary masks, and the other one is estimated binary mask estimated. So this model aims to learn to predict the binary mask, and then it can achieve sound separation using the audio and visual informations. So here is how to using different assumptions or different learning different models to learn the correlation between audio and visual correlations for sound separations. So in the last one, the last stage is how to directly learning to explore the relationship between sounds and vision for visual gate sound separation. Most of these approaches are based on deep networks. And the first one is how is you train the networks predict the using the manually mixed noise speech frames to predict the enhanced speech frames by fusing the audio and visual information in the middle layers, as shown in the figure in the left. It contains the audio and visual features in the middle layers, the merge layers. Then using the FC fully connected layers to predict the enhanced speech frames and reconstructed mouse images. And in the right image, we show that how to the input visual information can help to reconstruct the sound separation, sound spectrogram from using the input video information. It using the visual information for speech reconstruction, then you have to sound separation. So the most recent works consider that we can directly use the spectrogram mask from A1, the spectrograms, the manually from the manually mixed sound to help to training the deep networks. So by using the spectrogram masks, we can using the UNet, then use the property of UNet. It can help densely predict from the input spectrum to predict the binary masks to have some separation. So to achieve this, there are 3 steps. The first step is manually mixing different single source sounds, and the second step is computing the spectrogram mask for the mixed sound, and as the ground truth separation result. And the third one is designing audiovisual models for predicting the spectrogram of separated sounds. So under these 3 steps, there are different works, but that follow the same pipeline. And as shown in the left, it using the different speaker, using the single source of different speaker to generate mixed sound. And then using the mixed audio and the visual information concat in the middle layers. You train the model to predict different sources, such as the on-screen and off-screen signals, audio signals. And in the right, this works is more directly. It directly makes the sound, and in the left, and encode the image, and then concat the audio feature map and the visual feature map in the middle layers. Then you train the model to predict the sound separation result, such as that is train the model to predict the mask, then achieve the sound separation, audiovisual sound separation. So here is a demo for this. This left. So for the right one. This demo.
Okay, Google, please navigate to work. Okay, Google.
So here is the mixed sound, and we can learn how it's separated, the sound.
Okay, Google, please navigate to work. Okay, Google.
Okay, we can see that it can separate the sound and focus on the mom sound and denote the baby sound, and has shown great results. And the second one is if we have 2 person speaking, and we want to focus on the left one.
He's not on a Danny Ainge level, but he's above a Colangelo level. In other words, he understands enough to... If I
You said
were a
you said it was
Sixers
all right to
fan,
lose on purpose. You said it's all right to lose
yeah,
on purpose
yeah, of course
and
it is. It's called
advertise that to the
tanking.
fans.
Who doesn't
It's
know that?
perfectly okay. You said it's okay.
Yes.
We have nothing else to talk
Yes,
about.
So this is the original source. So if we focus on the left person, let's look at its separate result.
Don't explain it away now. Don't explain it away. You said it was all right to lose on purpose. You said it's all right to lose on purpose and advertise that to the fans. It's perfectly okay. You said it's okay. We have nothing else to talk about.
So you can see that this technique using the binary mask prediction, it can help to using by introducing the visual information, it can achieve a great separation result for the mixed sound from two persons. So apart from the speech separation, the researchers also want to separate other kinds of sounds, such as music sounds. So if we have different players are playing instruments, we want to separate different the sound for different players for different instruments. So this is music sound separation. So just like the speech sounds, the separation framework are not are similar. And in the left one, this model aims to learn the correlation in the feature level of the audio and visual features. And the right one is introduce the feature map for the sound separation by concat the feature map in the middle layers of the UNet for the spectrogram modeling. These two models also are the same. These two models also employ the binary mask prediction for training the audiovisual models. And apart from introducing only the static image, these two works also introduce the motion and the gesture to better modeling the motion information for visual model information, visual motion information for sound separation, and achieve better result than the static image result. So some researchers think that can we achieve better sound separation by introducing the vision information from other sounds related tasks. So in this works, the researchers propose to using the design a model to simultaneously achieve the sound separation tasks and the stereo reconstruction tasks by guiding by the vision information. And actually, the stereo reconstruction and the sound separation are share the same ways or share the similarity for when training the audiovisual networks. Basically, it assumes that the stereo reconstruction can help to sound separation. Meanwhile, the sound separation can also help to stereo reconstruction for in the sound processing tasks. So this works is still based on the feature map computation, just like the previous works. So here is some demos about the sounds, the instrument separation result. We can see that the model can show great results for the music sound separation when it seems different player are playing instrument. And besides the speech separation and the instrument or music sound separation, we also want to ask if we can separate the natural sounds for the real world scenarios, such as the baby is playing the drum. We can see that in this video the drumming is not always sounding, and there are multiple sounds such as the baby yelling and the mommy voice and the drumming sound. And we want to ask if we can separate the sounds, the drumming sound, the baby sound, the mom sound, and achieve better results. So this in this so for to solve this, to answer these questions, the researchers propose to build the temporal spatial feature clustering in each spectrum, and by importing the clustering techniques to figure out which part in the audio spectrum is related to different visual objects. Then it can help to achieve sound separation by clustering on the audio spectrum. So it's not based on the audiovisual feature map computation. It depends on learning the correlation of audio between the audio and the visual information feature maps by learning to align them. So here is some result, and we can see the demo result in here. So we can see that we can separate sound of the mom sound and the baby sound, and also we can separate the drumming sound in these real world scenarios. And I think it has shown great result in these natural scenarios. So this is overview. This is overview about the approaches in this under these topics. And finally, we will go summary about what are the core challenges and future directions about audiovisual sound separation. So in the past, the sound separation, audiovisual sound separation are based on signal processing or model based or learning based. I think in the future, the future direction to better address audiovisual learning, audiovisual sound separation, there are some challenges. First and second and third. So first one is for the learning-based method, they are based on the manually mixed sounds. It has the most problem of it is about computational explosion problems. If we can't mixture any two any two of the data set, any two sound of the data set, it's not reliable, and it's difficult to realize. And the second one is how to separate sound in the about the novel class. Not the class is unseen. The second one is complex natural sound. Because for the natural sounds, it has large intra-variance within each single classes. The second one is the object not always sounding, such as the baby drumming, the video, the example, and then we also suffer from the off-screen sound, because we cannot see the sounding object by so we cannot we can't import the visual information for sound separation. For the last one is the long tail distribution of sound class in uncreated dataset. So it is also important to be. It is also a challenging problem we should to address in the future. So here is the overview of here is a tutorial about sound separation about in the audiovisual scenarios. Thank you for listening.